In the boundless void of space where light bends and time stretches, James Webb Space Telescope has uncovered a celestial phenomenon that challenges the very foundations of our understanding of the universe. Since its launch on December 25, 2021, this incredible feat of engineering has been exploring the farthest corners of the cosmos. With a precision unmatched by its predecessor, the Hubble Space Telescope, Webb has become our most powerful eye on the universe. Its infrared vision allows it to peer through dense cosmic dust, exposing mysteries buried in the earliest epochs of space. And now, in the year 2025, it has recorded something truly astonishing, something that rewrites the rulebook on black holes. For over 100 years, black holes have been regarded as the ultimate cosmic prisons, regions where gravity is so intense not even light can escape. But Webb has captured an event that appears to contradict this unbreakable law, a flare not being drawn into a black hole, but emerging from it. Let that sink in. What was observed were rhythmic, structured pulses of infrared light coming from the edge of a black hole's accretion disk. These weren't random flashes, they followed a pattern, steady, pulsing rhythm echoing through space like a heartbeat in the void. Scientists are now grappling with what this could mean. Is this a new kind of natural phenomenon? Could it be quantum physics revealing itself at the very edge of a singularity? Or though it's whispered only cautiously, could this signal be something else entirely, something intentional? The discovery made early in 2025 has ignited a firestorm of scientific curiosity. But to understand the magnitude of this, we need to first look at the black hole at the center of the mystery. Black holes are born when massive stars die. Their cores collapse under immense gravity, forming singularities, infinitely dense points encased by event horizons, the boundary beyond which nothing escapes. This concept, predicted by Einstein's theory of general relativity in 1916, was confirmed with discoveries like Cygnus X1 in the 1960s, where X-ray emissions revealed the presence of a black hole. Over the decades, astronomers have observed stars orbiting unseen masses, detected gravitational waves rippling through space-time, and in 2019, captured the first-ever image of a black hole's shadow in the galaxy M87. Black holes are like cosmic vacuum cleaners, devouring everything in their vicinity: matter, light, even time. At the center of our own Milky Way galaxy lies Sagittarius A*, a supermassive black hole about 4.3 million times more massive than our Sun. Astronomers have long studied its swirling accretion disk of gas and dust, which heats to millions of degrees as material spirals inward, occasionally erupting in chaotic flares. But what Webb recorded in February 2025 was anything but chaotic. Using its near-infrared camera IR-CAM, Webb observed Sagittarius A** for a combined 48 hours over multiple sessions in 2023 and 2024. What it saw defied expectations. 5 to 6 major flares per day, punctuated by smaller bursts, organized, rhythmic, and structured. In a strange twist, flares of shorter wavelengths, 2.1 microns, appeared seconds before those of longer wavelengths, 4.8 microns. This timing difference wasn't random, it suggested a sequence, a delay pointing to an orderly process unfolding. Near the black hole, the flares were detected in mid-infrared first, for Sagittarius A*, and their near-mechanical repetition challenged the very notion that black hole behavior is inherently chaotic. This is where the shock lies. According to everything we know, nothing escapes a black hole. The event horizon is supposed to be a point of no return. Yet Webb's data seems to show something radiating from just beyond it, not plunging inward, but possibly being expelled. The pulses lasted just seconds, but were consistent and symmetrical, nothing like the usual irregular outbursts caused by magnetic reconnection. Those typically release energy in sporadic, unbalanced patterns. But here it was different, clean, structured, as if orchestrated. Farhad Yousefzad, an astrophysicist at Northwestern University, described the black hole's behavior as bubbling with activity, but never in a steady state. Every observation revealed something new. Bursts of brightness would appear and vanish in ways that felt almost deliberate. And the consistency of the pulses, their timing and energy suggested coherence, not chaos. Some likened it to a cosmic Morse code echoing from the depths of space in the form of infrared light. Scientists have ruled out typical explanations, like debris collisions or large-scale plasma jets. The timing, frequency, and energy of the pulses simply don't align with those phenomena. So what could cause it? One possibility is a form of quantum behavior near the event horizon. Black holes exist at the crossroads of general relativity. In quantum mechanics, a place where our current models break down. Some theories suggest that subtle quantum gravitational effects near the event horizon could produce exotic emissions, visible only in the kind of detailed infrared data Webb can collect. Another possibility is tied to the turbulent dynamics. Within the accretion disk itself, small instabilities might compress and release energy in rhythmic bursts. But the sheer precision of the pulses casts doubt on this. Nature doesn't usually operate like clockwork. This leads to a more speculative, though increasingly hard to ignore theory. Could these emissions be signs of a white hole or a wormhole? White holes, theoretical opposites of black holes, would emit matter and energy, but not allow anything to enter. In certain models of rotating black holes, it's possible, though still unproven, that energy could be funneled through an exotic region of space-time and escape in brief pulses. The structured pattern Webb observed could, in theory, align with this. Wormholes and white holes remain hypothetical, acquiring forms of matter with negative energies, something we've never observed. Even so, Webb's observations have given physicists a window into conditions so extreme that space-time itself may behave unpredictably. One theorist even suggested we could be witnessing a crack in the cosmic fabric, a place where something unknown is slipping through. The scientific community's response was immediate and intense as soon as Webb's data was made available. In early 2025, astronomers around the globe launched a coordinated investigation. Conferences erupted with speculation. Academic papers flooded journals. Teams raced to compare the infrared data with X-ray readings from observatories, like Chandra, and radio signals from facilities such as ALMA. Their goal: to catch the same flares across multiple wavelengths and triangulate their origin. Summarize the feeling. This isn't noise. This is orchestration. Even skeptics who initially dismissed the pulses as errors or artifacts were struck by the data's precision. SETI researchers quietly filed the signal into their anomaly databases. While there's no decipherable message, the pattern itself bears similarities to modulated transmissions like Earth's own broadcast signals. Could an advanced civilization be harnessing black hole energy? Could a structure possibly something akin to a Dyson sphere exist not around a star, but around a black hole? Such an idea, though speculative, has been floated. A civilization capable of such feats might use a black hole's spin to generate power or send beacons across space. To be clear, there is no evidence of intent or communication, no code, no message. But the regularity and precision of the pulses raise important questions. If we dismiss the unusual too quickly, we risk overlooking discoveries that matter. Whether natural or artificial, these flares force us to consider possibilities that were once relegated to science fiction. In response, researchers and engineers have stepped up their efforts. In 2025, Webb was granted extended observation time to continue monitoring Sagittarius A*. Its infrared sensors were enhanced to detect even the briefest temperature spikes. A real-time alert system was developed if Webb detects a flare. Telescopes on Earth instantly pivot to observe the same region in different wavelengths. This international collaboration transforms Webb from a passive observer into the leader of a global astronomical campaign, and the stakes are high. If these pulses turn out to be natural, they could help us uncover new physical laws. Bridging general relativity with quantum mechanics, a dream Einstein himself never realized. If they're artificial, the implications are staggering. We might be witnessing technology so advanced, it's indistinguishable from nature, civilization capable of manipulating space-time itself, regardless of the outcome. The journey has already changed us. Scientists, observatories, and institutions around the world are united by a single mystery. It's a powerful reminder that discovery is driven not by certainty, but by curiosity. black holes, once thought to be the universe's final destination, may instead be portals, gateways to something beyond our comprehension. And Webb, with its golden mirror reflecting the cosmos, has cracked that door open. As we stand on the edge of this new frontier, questions echo across the cosmos. Are these pulses simply a natural process we've never witnessed before? Are they glimpses into the quantum nature of space-time? Or could they be signals, intentional or accidental, from a mind far beyond our own? One thing is certain, this is not the end of the story. It's just the beginning. The universe has presented us with a puzzle, and humanity is rising to meet the challenge. As Webb continues to watch the darkness, we wait for the next flare, the next clue, the next step into the unknown. So what do you think is pulsing out there in the shadows?